Welcome back. So in the previous topics we were discussing about the stresses in the bending and the shear force and the bending moment. Then we have discussed what should be the assumptions and how the material should have to behave for the bending equation theory. So next we're going to discuss about the Euler and the Bernal bending equation. So they derived an equation. So that we're going to use further to find out this Euler and Bernal bending equation. That is what we call it as a flexure formula. So that is the where you can able to see this formula, that is m by I will be equal to f by y will be equal to E by R. So this is where the Euler and the Bernal bending equation, that is what we're going to call it as a flexure formula. That is where we're going to use this equation to find out the forces. So what do you mean by any? Will now we will see the notations of each one. So M is nothing but a resisting moment developed inside the material against the applied bending moment, and it is numerically equal to the bending moment applied. So normally M where we're going to consider M as a bending moment where when it comes to the SFD or BMD. So the resisting moment developed inside the material against the bending moment. When the bending moment takes place, when you're going to apply the load, so automatically what happens, deflection, the deflection we're going to get, that only we're going to consider as a bending moment, and is numerically equal to the bending moment applied. Yes, that is the unit is Newton per millimeter, and the I is nothing but moment of inertia of cross section of beam about the neutral angle. I is nothing but a moment of inertia of cross section. Cross section is nothing but where the area where we are going to apply the load, and F is nothing but a direct stress that is developed in any layer of the beam. So F is nothing but direct stress, whether it might be in a compression or whether it might be in a tensile stress. So when it is developed in any layer of the particular beam. So next where y is nothing but a distance of the layer from the neutral axis. So neutral axis, from the neutral axis, the y is nothing but the distance from the layer, that is distance of the layer from the neutral axis. And next is nothing but E is nothing but an Young's modulus or modulus of elasticity of the material of the beam. So the E is nothing but material of the beam of that, whether Young's modulus or a modulus of elasticity, and R is nothing but a radius of curvature of neutral layer. That is R is nothing but a radius of curvature of the neutral layer. This is what the equation, that is Euler or Bernal bending equation, that is M by I will be equal to F by Y will be equal to ER. So by equating all this, we can able to find out the unknown unknown content or unknown equations. By using this equation, we can able to identify that by using this flexure formula. So next we're going to see about the derivation of a relation between the bending stress and the radius of curvature. So this is what we call as a relation between the bending stress and a radius of curvature, where you can able to see this diagram, where the axis, that is n, where you can able to see the y is nothing but a deflection where point E and B, and where dx is the distance. So this is about the bending. When what happens when the bending, the second diagram indicates that is a curve, that is radius of curvature, that is how the curve will be formed. So that is where you can able to see that is angle theta, and the R is nothing but a radius of curvature from the point O, and these are neutral axis where you can able to see, and the points varying from A1 A dash to B dash, C dash and the D dash. So now what we are going to consider is relationship between the stress and the radius of curvature. Consider a small length, that is delta x, of a beam subjected to a simple bending. So here just we are going to consider one of the simple bending as shown in the figure, that is dx, or what we have taken as the delta x of the beam subjected to a simple load, that is simple bending load. Due to action of bending, the length delta x will be deformed as shown. That's what this is what the deformation. See, when we're going to apply the load on this, so it takes as a deformation. So this deformation only we have written, that is in the form of curve, where you can able to see this is a deflection of y. So that is the deformation which is taking place, that has been shown in the figure 2. Now considering the two sections very closely, that is what considering the figure A and B, AB and CD. After bending the sections, it will be from A1 to B1 and C1 to D1, they will be parallel. So hence we will be having a such, so it will not change in the length, but the surface of the neutral layer and the interaction will be called as, that is what the neutral axis that is been developed. So this development lines, what happens, that is A dash, B dash and C dash intersect at point O, where you can able to see this A dash, B dash, C dash and D dash all these points will intersect at point O, where you can able to see at point O. So that point where they are going to intersect, and the angle of theta is radians, and the radius, that is E1 by F1, will be equal to R. So you can able to see this E1, that is E and F, will be equal to R. E and F will be equal to R. R is nothing but a radius of curvature, that is the deflection which is taking when we apply the load. Now let y be the distance, that is the y will be the distance from the EG of any layer H and G originally, then it is parallel to EF. Then H1 G1 by E1 F1 will be equal to R plus Y into theta. Theta is nothing but the angle, R is nothing but a radius, and Y is nothing but a distance from the neutral layer or neutral axis. So when we substitute, we are going to get R plus Y by R. Again, see this theta is going to get cancelled. Now the remaining is R plus Y by R. R is nothing but a radius of curvature, and Y is nothing but a distance. And the strain at this layer from the point H1 and G1, when it's again R plus Y into theta minus R into theta by R into theta. So now the deflection what we are going to will be equal to Y by R. Again, Y is nothing but the distance from the neutral layer to the deflection, and R is the radius of curvature. Now the relation between the stress and strain is will be equal to, where you can see the stress and strain is nothing but stress will be equal to strain. When the stress will be equal to strain is nothing but when stress will be equal to strain, that is strain into Y by R. So when we consider Y by R is nothing but, so sigma by E will be equal to, that is stress by strain will be equal to Y by R. So the relationship between the stress and strain is nothing but E, that is whether you can consider modulus of elasticity or an Young's modulus. Now sigma will be equal to E, and E will be E into Y by R into sigma by E. So that sigma by E will be equal to Y by R. So this is what the relationship between the stress and strain, that is what we are going to occur. Now when we consider in a small elemental area dA at a distance y from the neutral axis, same when we consider the same. So what happens when you consider the dA, that is at from one point the distance elemental area for that cross section of at any one point with the distance of y, what would be the section modulus? That section modulus is nothing but F will be equal to m by I. M is nothing but moment, and I is the moment of inertia, and y is nothing but a distance. When you find out the F max, that is m into, when you cross multiply, so m max by I into y max. So totally now what we are going to get is nothing but, for the section modulus, m max will be equal to F max into Z. So this is how we are going to consider for the polar. Now coming to the section modulus of the beam is nothing but the ratio of moment of inertia of the cross section of the beam about the neutral axis. So that is when we need to find out the section modulus for this same beam. So that is Z. This the equation is nothing but Z will be equal to I by Y maximum. So which is a Y is nothing but a distance which is a maximum we are going to consider, and I is nothing but a moment of inertia. For more the section modulus, more will be the moment of resistive moment carrying capacity of the beam for the strongest beam. So this is the section modulus must be the maximum. So this is how we are going to consider for the relationship between the bending equation and the radius of curvature.